My name is Tim Johnson, and my work seeks to understand how subsurface processes evolve using time-lapse geophysical imaging.
Hello there, my name is Andrew Gary, and welcome to Seismic Sound Off In-Depth Conversations in Applied Geophysics. In this episode, Tim Johnson discusses his article in August, The Leading Edge, about real-time electrical resistivity tomography. Time-lapse electrical imaging has been used for diverse scientific and engineering problems to monitor changes in the subsurface. Tim and his co-authors posit that the next step in the evolution of time-lapse electrical imaging is autonomous, real-time monitoring, which has the potential to support real-time management decisions and feedback control of subsurface systems. In this conversation, Tim presents a framework for autonomous real-time electrical imaging. He also shares 2 case studies of the framework in action and potential areas of development for this work. This forward-looking conversation utilizes machine learning and the latest electrical geophysical instrumentation to highlight what the future can be for hydrogeophysics. Let's get to my conversation with Tim Johnson. A great introduction to what we're going to be talking about here today. So you published in August, The Leading Edge, an article about autonomous time-lapse electrical imaging. And to kind of start with a little maybe historical lesson, how did the advances in electrical geophysical instrumentation and data analysis help create the basis for the subject of your paper?
Yeah, sure. Both of those were important. The electrical geophysical imaging started by people just using, 4 electrodes. They were actually metal probes they would stick in the ground manually. And over the years, it advanced to systems where many, many electrodes were connected to the ground using cables, and those cables were connected to instruments that took measurements autonomously, so that there was really once an array was installed, there was no effort from humans to collect data. It would just do so automatically. So that enabled time-lapse imaging to happen autonomously. So that was an important development in that. And another thing that enabled real-time was the advent of processing the data on supercomputers, which allowed you to process the data fast enough that the data processing occurred faster than the data collection. So those 2 advancements are what enabled what we published in the paper.
So how did developing time-lapse electrical resistivity tomography, and we'll refer to that a lot as ERT throughout this conversation, improve its utility as a geophysical method?
Yeah, well, so in ERT, we're imaging the electrical conductivity of the subsurface, and that electrical conductivity is governed or controlled by a lot of different things. So when you take a static image and you look at it, you see changes, but it's very difficult without some other information or knowledge to identify why those changes are occurring in space. In time-lapse imaging, you're subtracting out all of the things that don't change, and you're only seeing the things that do change over time. And usually you know what that is, what it is that's changing. So that makes time-lapse imaging really useful because you can track things moving through the ground, for example, when and where things are changing. And that's really valuable information. And another reason it improves the utility is because you can see very, very small changes. So things that you can't necessarily see changing in an absolute image, you can see very easily in a time-lapse images. So for those 2 reasons, it's really improved the utility of ERT.
The real-time ERT is very central to this paper, and I thought it interesting and helpful that you defined it in the paper itself. So that could be a helpful place to kind of start here with it. How do you define real-time ERT?
Well, people might define it differently. I defined it in the paper as the capability to autonomously process the data faster than you can collect it. And there might be other ways of defining it, like, because in some sense, real time depends on how fast the process is happening that you're trying to monitor. But for the purpose of this paper, it was just faster than you can collect the data.
What are some of the unique challenges when working with real-time ERT?
Well, one of them is the computational challenge, is processing the data and automating things. But the real challenge, as I pointed out in the paper, is that when you're doing real-time ERT, you don't have an opportunity to go back and adjust how the data are being processed. Usually in geophysical imaging, there's a lot of iteration that you do to try to get the best image. And in real time, you can't do that because you've already lost the opportunity if you have to go back and change the settings. So one of the biggest challenges I found in trying to develop and refine the approach was how do we get the correct settings before the time-lapse imaging campaign starts.
Well, it seems like maybe one of those ways was using Python scripts to address those challenges. How did you utilize these scripts to address this unique challenges facing real-time ERT?
The Python scripts didn't necessarily address the problem of getting the settings right, but they did address the automation part. So the Python scripts are really kind of the glue between the field instrument and the supercomputer, and then on to the website where the data are presented, or where the images are presented. So they kind of link the field to the supercomputer to eventually the user interface.
What do you consider the most challenging aspect of implementing effective real-time imaging?
It would be the thing I mentioned before, and that's getting the parameters set correctly, the data processing parameters set correctly before the imaging campaign. There are just a lot of issues and challenges with doing that, especially if the noise in the data changes over time. How do you deal with that? Because that can really affect the quality of the images. What happens if some data drop out, or the instrument, some electrodes lose connections or things like that? How do you deal with those things? That was really, once the computational challenges were addressed, that was really the hardest part of enabling real-time imaging.
Well, you provide some real life case studies in this paper as well. What is the sort of 50,000 foot overview of the two case studies that you present in this paper?
Yeah, there were two of them, and both of them were environmental remediation applications at the Hanford site. The first one was a soil desiccation study of the vadose zone, and really that just involves drying out the vadose zone so that the contaminants can't move downwards, or they move downwards much more slowly to the water table. So you're having a contaminated subsurface, and you're really trying to reduce the contaminant flux to the water table, because once it hits the water table, it becomes much more mobile. So by drying out the soil, you reduce the rate of downward transport of the contaminants, and therefore reduce the flux rate to the water table. So that was the first one, and the second one was similar. We had vadose zone contamination, or uranium contamination, and in this case, the cleanup contractors were testing a chemical amendment called polyphosphate that they injected, and the polyphosphate basically co-precipitates the uranium contamination and binds it to the soil so that it can't move. It's kind of frozen in place, and if it's frozen in place, it's not moving to receptors, so it's remediated, or considered remediated. So those were the two applications that we were using the time-lapse imaging for.
Why is real-time tracking particularly useful in these two case studies on environmental remediation?
Well, the autonomy is one thing. When you make things autonomous, they're much less expensive to operate and implement, and much more useful, because you just take the human component out. The real time in particular was useful because it provides a feedback mechanism for the contractors to be able to adapt their process while they're there. So typically, a contractor, for example, the chemical injections for the uranium remediation, without the ERT, they would have went and injected the chemical amendment, and they would have not known where the amendment went, right? Until they go in afterwards, and they have to basically drill boreholes afterwards to try to get an idea of where it went, and therefore how it performed. If they know where that is in real time, they can adjust their operations to optimize the treatment while they're there. Where if they don't have the real time imaging, they don't have the opportunity to do that. So it really provides a feedback mechanism for them to be able to optimize the treatment.
What do you find as some of your hesitations in using autonomous cross-hole ERT monitoring in deep subsurface processes?
Yeah, so there are a lot of challenges in the deep subsurface that we don't have in the shallow subsurface. I mean, and first and foremost of those is the prevalence of steel casing. So we can't use ERT with steel casing. In the shallow subsurface, the pressures and the stresses aren't near as high, so you can use plastic or PVC casing and put electrodes on that casing. In the deep subsurface, everything's steel for the most part, and so that there's a big challenge there. There are ways to address it, but there's a big energy involved with convincing people to do that. I mean, the benefit the benefit that that operators would have to see to change their casing to, say, fiberglass or a coated casing, the benefit has to be pretty large before they would be willing to do that. And I believe the benefit is there. It's just a matter of having the opportunity to test and demonstrate. So in the deep subsurface, it's just a new technology that hasn't been used much at all, and there's some development and demonstration to be done to remove the risk.
You state in the paper that real-time imaging has potential applications beyond the environmental remediations projects highlighted in this paper. What might be some of those other applications?
Yeah. So, I mean, one of them is applications in the deep subsurface. So we've recently demonstrated ERT for monitoring changes in stress associated with high pressure injections into crystalline rocks. That was for a geothermal application. We're using it also in the national security space to monitor how underground explosions damage the subsurface, which has important implications for understanding how to detect signals from underground nuclear explosions. So those are two applications beyond environmental. We're also using it for leak detection at nuclear power plants. That's still kind of an environmental application, but it's a little different than the typical one. But so there's great potential in the deep subsurface, the energy applications and the storage applications for carbon sequestration. ERT's actually been tested quite a bit for that. So it would be the deep applications where I think the most new impact could happen with ERT.
What are a few areas of potential development for this future of this work that has you excited?
Me personally, in the last maybe half decade or so, have started using this application in geothermal energy and in carbon sequestration. And I think moving forward, I think ERT monitoring, because the sensors are robust, they can be made easily to survive in challenging conditions that exist in the deep subsurface where other sensors and technologies can't do that. They can be hidden behind the casing so that the boreholes are used for other applications. If we can get over the energy required to convince operators or people of the utility of time-lapse ERT in the deep subsurface, I think it can have a tremendous impact there.
This is always one of my favorite questions. Did any new questions come up to you or that you discovered after finishing this paper?
No, I wouldn't say I didn't have any new questions. I did have some interesting perspectives from some of the reviewers who actually work in the deep subsurface applications in terms of their perceptions of ERT and what would be required and what it could and couldn't do in the deep subsurface. Because I usually work with shallow subsurface people in the environmental applications, so it was interesting to get some other perspectives from the reviewers of the paper.
And kind of lastly here, a more general and practical question for others. What principle, teaching, or point of view has helped you succeed in your field?
Gosh, I would say tenacity. Don't give up. Just grit and tenacity. I mean, I think people will have a good idea, and if you have a good idea and you know that it can be useful or have impact, just work hard and keep pushing on it. If it was easy, somebody would have done it already. But just believe in yourself and have tenacity, I think, and grit and keep going. That's something that's served me well in my career. So,
yeah, that's a good place to leave it there. Tim, I appreciate you coming on. We'll link to your article in August, The Leading Edge, as well as the rest of the special section. And best of luck as you continue to discover what you can do with real-time ERT.
I appreciate that. Thanks for the opportunity to talk.
SEG produces Seismic Sound Off to benefit its members, the scientific community, and inform the public on the value of geophysics. To show your support for this show, please leave a 5-star review on Apple Podcasts and Spotify. Simply go to Seismic Sound Off on Apple Podcasts and Spotify on your phone. It takes less than 5 seconds to leave a 5-star rating and is the #1 action you can take to show your appreciation for this free resource. And follow the podcast while you are on the app to be notified when each new episode releases. Original music created by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Gary at 51 Features. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.